My name is Marco Dorigo, and I'm co-director of the Artificial Intelligence Laboratory of the Université libre Bruxelles in Belgium. In this video, I'm going to present the results that we obtained within the context of the RoboCom project. In particular, I will talk about the RoboSwarm with mergeable nervous systems. So the problem I'm interested in is how to control a large number of robots, what we call a RoboSwarm, so that the robots cooperate to perform a given task, and that the swarm is robust to failures, is scalable. Where scalable means that we can change the amount of work produced by increasing or decreasing the number of robots without the need of reprogramming the swarm as a whole. This is, I think, an important problem, because in the future, there will be, for sure, more and more robots that will share with us the environment, so we need to know how to control these large number of robots. So when you think about controlling a robot swarm, there are basically two possible extreme approaches. One is centralized control, where there is one central controller that can be a computer, can be one of the robots in the swarm, can be a human, that has full knowledge about all the system components, so all the robots that are in the swarm, and that is in charge of controlling them. In favor of this type of approach is the fact that we have a lot of experience on how to program centralized systems. However, these systems have a single point of failure, because if the central controller fails, the whole swarm doesn't work anymore, and this is difficult to scale. So it is difficult to change the amount of the level of performance, the amount of work produced by simply adding or removing robots in the swarm. On the other extreme, there is self-organization, where there is no centralized control, because the control is distributed over the system component. There are only local interactions between the robots and their environment, and only local communication between the robots in the swarm. This approach is coherent with our goals of having a robustness to failure and scalability. However, there is a problem, what is called the micro-macro problem, or micro-macro link problem. So the problem is how to program the single robot so that the swarm behaves as you want. This is difficult because while the goal is to program the swarm as a whole, you can only program the single robot. Okay. So we've been working in my lab for many years about the self-organized approach, and we have come up with rather complex systems like the one that you see in this video, where a swarm of robots cooperate to find and retrieve a heavy object, and where each robot is programmed with a simple finite state machine like the one that you see on the left, and there is no centralized control. So even though this is very interesting results, what we have found is that it is extremely difficult to extend these, to increase the complexity of tasks that can be performed by a swarm with this type of approach. So lately, what we have tried to do is to go beyond the pure self-organization approach, and to introduce elements of centralization in the organization of a swarm without losing the benefit of self-organization. And this is what we call the robots with mergeable nervous system. So let me first introduce some terminology. What we call a robot's nervous system, it's a CPU and signaling architecture. So what you see is the schema of a robot. The brain of the robot is basically it's a CPU, and its nervous system is a CPU and the connection between the CPU and the sensors and actuators. Okay? So now, when you have a robot that is endowed with a mergeable nervous system, what happens is that if there is a second robot that connects to it, when connecting, it cedes authority to the robot to which it connects to. So what you see here in this, here is that the robot on the left, at the moment of attachment, it cedes authority to the other one. So now we have logically a single robot. Well, it is a single robot because it's made of two robots that were individual robots before connecting to each other, and now they are physically connected to each other, but they are not only physically connected, but they also share a common nervous system. So there is a single brain because the brain of the robot on the left is given authority to the robot on the right. Okay, when you have this type of middleware that allows robots to connect to each other to form bigger robots and to share their nervous system, you have some interesting properties. So what you see here is a robot made up of 6 component robots. And the robots in red is the brain. And the brain has knowledge about the topology of the component robots that are attached to it. Okay, so that you see in the figure below. And each of the robots within the body has knowledge about all the children that are attached to it. So when you have 2 such robots, 2 MNS-enabled robots, and you let them attach to each other, for example, the robot on the left is attaching to the robot on the right, the brain D, when it attaches to the robot C that you see on the right, okay, it transmits all the information about the topology so that the brain A has immediately knowledge about the topology of the new body. Okay, so because of this architecture, the robot can exhibit interesting behavior. So let's consider, for example, a point-and-retreat behavior, where a stimulus, the robot have to point by lighting up their green LEDs a stimulus that appears in the environment, and when the stimulus is too close, they have to retreat. Okay? So this is a quite easy behavior to be implemented on single robots. Now, let the robot attach to each other to form bigger robots with a single brain, with this mergeable nervous system idea. When the stimulus appear now, only the closest part of the body lights up the green LEDs to point to the stimulus. And this would be something very difficult to do in a pure self-organized way. And here is possible because there is a brain that knows about the topology of the body. Here now the 2 robots have attached to each other to form a new, bigger robot. And again, the stimulus appear, and you see that the robot, composed now of 9 component robots, is able to react as a single unit to the stimulus. Okay, so this mergeable nervous system idea does also allow to have a nice property of self-healing that you see here. So now we have a certain number of robots that are given the command to connect to each other to form a given shape. And then we induce a failure into the brain robot. So the robots that are attached to the brain robot realize that the brain is broken, and so they detach and reattach to repair the shape. And this works not only if we induce a failure in the brain, but also if we induce a failure in one of the children robot, in one of the body units. So in this case, we have we induce a failure in one body unit, and the brain realizes, it moves away, it attaches, moves away, and then if there are spare parts, new body units can attach, and the bigger robot is repaired. So this is work that was done in collaboration with one of my PhD students and some other colleagues, and is at the starting point for the work that we have done in the RoboCom project. So what we've done in RoboCom has been to try to extend the MNS concept to swarm robots that are not physically connected, and also swarm robots that are heterogeneous, in particular composed of ground and flying robots. So in our example, we consider ground robots and flying robots. The ground robots can avoid each other, and they can communicate with flying robots using Wi-Fi. And while the flying robots can see the ground robots and compute their relative position and orientation. So what the overall goal of the swarm is to keep a predefined shape while moving around. So you see the shape that we want on the left, and you see the how the MNS architecture is once formed, with the rightmost flying robot as a brain. So what happens is the following, that each robot starts in brain status, and then when a flying robot sees a ground robot, it tries to recruit it in the forming mergeable nervous system. Okay? And it does so if it is not already recruited. On the other side, if a ground robot is already recruited, for example, imagine that FK, the flying robot FK, tries to recruit GK, the ground robot GK, it is already recruited, then there is an exchange of messages between these robots. And the end solution is that the flying robot that was the owner of GK also recruits FK. And this way, the mergeable nervous system is created. So I'm not going into the details here, but you see that by applying this reasoning a number of times, what you get finally is the desired shape with with one brain and all the other children that belong to mergeable nervous system swarm. So the process of building this mergeable nervous system goes up in parallel, go up in parallel. And so whenever the robots meet in the environment, they can merge and form sub-part of the mergeable nervous system. And if the area in which they move is bounded, then you can prove that the system converges to the desired shape. Okay, so as it was the case in the previous work, you can show that the system is robust to failures. So you can have a failing brain, and then you can send a new flying robot, and the shape is reformed. Okay. Similarly, you can displace a ground robot, and then the system replaces the ground robot at the right position, or similarly for a flying robot. And okay, so this is the main result that we obtained during the RoboCom project, and that's been recently published in collaboration with these people that are my PhD students and postdocs, and with Anders Christensen, that is professor in Denmark. And so what next? The next step will be to demonstrate this mergeable nervous system for a heterogeneous swarm using real drones and ground robots. So what you see here are the prototypes of these robots. We are already running some initial experiments with the drones. And so to conclude, I would like to say that I believe that in future, there will be more and more robots around us. There will be robot swarms that will be heterogeneous, so made of many different types of robot, and that these technologies, these robot swarm with mergeable nervous system, is a significant step towards real-world deployment. Why? Because it retains the scalability and fault tolerance of self-organized systems, which are very desirable, but are easier to program, are easier to interact with, and can exhibit self-repair capabilities. So if in case you are interested to know more about my research, you can find a lot of information at my own page, including articles, and you can watch 2 nice movies about swarm bots and swarmonaut. Thank you.